The light coming from different stars has different colors, where the radiance, as a function of wavelength, will look something like this. These are real stars. This is Spica, which burns at 23,000 Kelvin and happens to be located 261 light years away from the Sun, which is this one. And this one is Antares, which burns at a nice cool 3,400 Kelvin, located 620 light years away. Our goal here is to use statistical mechanics to find how the emission spectra depends on temperature. Because it's light, any statistical analysis is being done on light. And how do you treat light? You treat it as a photon gas. If you just imagine a container full of light, this poorly drawn box is filled up with photons. The expectation value for the energy of the photons in this gas of photons of some frequency can be written in terms of the Bose-Einstein distribution. And this is expectation value of photon energy. If the photons are generated with a frequency of omega, that is an average energy of h bar omega, they're distributed by the Bose-Einstein distribution. 1 over e to the h bar omega divided by Boltzmann's constant T minus 1. H bar is Planck's constant over 2 pi. K is Boltzmann's constant. And this 1 over e to the h bar omega over kt minus 1 tells you the occupation number of photons at a frequency omega emitted by matter at temperature T. And light that comes off of matter at temperature T is a gas of photons. They all have speed c, the speed of light in vacuum. Let's go back to this cavity that contains the gas. Draw out the 3 directions here. You have your x direction, the y direction, and there's the z direction. Each side of the cavity has a length L, and it is at a temperature T, and there are photons inside. Now the cavity is empty, it's vacuum. Its walls are reflective, perfectly reflective. So when photons are inside this cavity, if they have a wavelength that is commensurate with the length of the cavity, it resonates. And we can draw those resonant modes. There's the first order mode. It'll be at the lowest frequency, called frequency 1. Then there's the next mode, and the next, and so on and so forth up until a very high number. Photons inside the cavity are produced by the vibrations of atoms on the surface of the metal walls. That's simple harmonic oscillation. And the photons can go in all directions inside the cube, like gas molecules would do, and they're limited by the walls that stop them. These resonant frequencies of the cavity are determined in the same way that resonant frequencies for a vibrating string are determined. It's a 3-dimensional particle in a box. I'm going to scribble up here the speed of a wave is its frequency times its wavelength, and in terms of angular frequency. And we'll write the resonant frequencies for this cavity. Omega 1, the first resonant frequency, corresponds to twice the length of a single side of the cavity. So it's 2 pi times frequency, where frequency is c over lambda, where that first wavelength is 2L. And the next mode resonates at, you can figure out, 2 pi c over L. And the third one, again you have 2 pi c divided by the wavelength of the third one, which is 2/3 L, or 3 pi c over L. You see the pattern, that the resonant frequency for each of these modes in the cavity is an integer times pi c over L. So the separation between neighboring modes, rather the free spectral range of the photon gas, n plus 1 versus n, it's just pi c over L. This cavity is drawn in configuration space. That is, we're literally looking at its physical dimensions in x, y, and z. It's worth mapping out these modes, not in x, y, and z space as they're sketched, but rather in terms of their frequencies. Where omega sub x, y, and z are the frequencies exhibited in the x direction or the y direction or the z direction. A photon does not have to have the same omega in each direction. I'm going to draw some lines here on the omega x, omega y plane. And the spacing between these lines is pi c over L, go back and look at the resonant frequency condition to see why that is important. It's this pi c over L right here. And I'll draw a series of lines on the omega y, omega z plane. And they're also spaced by pi c over L. And finally, and they're spaced. I can draw more lines. Again, back to the omega x, omega y plane. And yes, they're spaced pi c over L. And at each one of these intersections, I'm going to put a dot, because that represents an actual mode. The space is filled with these dots too. They're not just residing on the planes, in the omega x, omega y, omega z planes. They are residing in three-dimensional omega space. I'm going to draw a spherical shell. That's an octant of a sphere. Now let's make it a shell. And it has a certain thickness to it. I want to ask how many modes there are in a unit volume of omega space. Each dot is a mode. How many dots are in a unit volume of omega space? And for that, we're looking at the density of states. The density of states is the number of modes per omega, the number of dots per omega. So if I have a unit omega, perhaps defined by this spherical shell, the number of dots inside would be the density of states. I'm going to define it with a word equation. The density of states, the number of states per volume in omega state, G, times an increment of omega, so if I took the volume of the spherical shell in this space and divided it by the volume of each mode, I would have the number of modes. Now it's an octant, so I need to multiply it by 1/8 because it's easy to calculate the volume of a spherical shell. Do that and then divide by 8 to account for the fact that these omegas are only positive. Something less obvious is a factor of 2 that needs to be included, due to the fact that all electromagnetic waves are composed of two orthogonal polarizations. For example, a plane wave has an electric field in the x direction and a component of electric field in the y direction. There are two perpendicular directions, and so that's the multiplicity of each state in the photon gas. With that little correction of a factor of 2, I will put in a few things that seem evident from the graph. First, the volume of a spherical shell is just its area, 4 pi radius squared, times the thickness. So d omega is the thickness, and the radius, let's try to draw this in 3 dimensions and see if it's convincing, to the surface is omega, divided by the volume of a single mode. So pi c over L is a single dimension, so you need 3 of those, times 1/8, and finally gives us omega squared times L cubed, which I'm going to write as V, shorthand. So if you go back to my video on the Sommerfeld theory of metals, you'll see the exact same series of arguments being used for the density of states of electrons conducting through a solid. And this is written as a function of omega, but suppose you want to be in lambda space. If I did this in terms of lambda, I have to get the same value. In fact, if I use wave number, I have to get the same value. The way you do these translations is use the argument that omega is Kc in order to substitute out what you need. Change omega to Kc. Now we can figure out the energy of a photon gas. We'll use the letter U. And when we do this, we're going to want to specify the emitter's temperature rather than omega, but they're related to each other. So the energy of a gas of photons is the energy of a single mode times the number of modes. What does this give us? This tells us how much energy a photon gas contains for the photons that happen to have frequencies around omega in the range of d omega. Integrate that out over all omega, you have the energy contained in a photon gas. So we found an expression just now for g of omega. We already determined that this, the energy of one single mode, which we also called the expectation value of U, is the Bose-Einstein distribution. So let's write this out. Well, remember, V is L cubed, where L is the size of the cavity that the gas is contained in. So V is the volume of the cavity that contains the gas. Some shorthand, the integrand, except for the V, is often called little u sub omega. It's the spectral energy density. This is an integral, and as such it can be solved, but it's not a trivial integral to solve. We can rely on some special functions to get it. If you want to skip ahead to having the solution, go ahead, but I'm going to write this out a few more steps here. This is called the Bose integral, where n is the exponent on the independent variable. And it equals the product of two special functions, the zeta function and the gamma function. In this particular case, we're dealing with the exponent n of 3. And the zeta function of 4 is pi to the 4 divided by 90. And the gamma function of 4 is 6. So pi to the 4 over 15 is the value of that integral, which then finally leaves us with u equals... Temperature was not an integration variable, and this k to the 4th, temperature to the 4th, is a consequence of the u sub that is necessary to make this integral look like the Bose integral. Something I always like to do is multiply my answers by 1. And my choice of 1 today is 4 divided by 4, because that gives me the parentheses is the Stefan-Boltzmann constant. This is the Stefan-Boltzmann law. It may not be in the form that you usually see it. Let's write it in the form of exitance. If I have a surface that's emitting, photons come out of the surface and they go in various directions. Random orientations. Rather than having this be the energy contained in a photon gas, I want it to be power per unit area, the exitance, in watts per square meter, instead of energy, which is in joules. I'll draw the surface as a two-dimensional surface. It has a certain area to it. Photons are leaving into a volume. And the distance that I'm depicting here in the vertical direction is the distance they go on average per unit time. If you take the volume V of the cavity and you divide it by the speed that the photons are traveling, what you have is the area times time. It has dimensions of meters squared second. Area times the amount of time it needs for photons on average to travel through this dotted box is V over C. Almost. Except that the photons aren't all coming out straight. They come out at random orientations. And so the average speed of a photon heading away from the surface is the speed of light over 2. So if I want the exitance, which is joules per second meter squared emitted from the surface, take the rate that energy is leaving the surface per unit area, where A times delta T is V over 0.5 C. And you're almost done. One more piece of the argument to be made. A photon emitted at the surface could be heading out of the surface or into the surface. So you still lose half of them. Half of the photons are gone, half of the energy that's emitted is gone. Now we're done. So now write the exitance this way. Delta U is 4, V over C, Stefan-Boltzmann constant, temperature to the 4th, over V over 0.5 C times 1/2. The 4 cancels with the 1/2 and the over 0.5. The C's cancel and the V's cancel. So the radiant exitance is the Stefan-Boltzmann constant times temperature in Kelvin to the 4th. Let's go back to the spectral distributions of these stars and look at why the radiance has a maximum where it has for each star and why it's temperature dependent. Going back to the spectral energy density, it's really a simple question of asking where is it a maximum. And we'll look at it in frequency domain instead of wavelength domain. Take the derivative of the spectral energy density with frequency omega, set it equal to 0, and solve, and you get this transcendental equation. You can solve it iteratively. In another problem, which would be another video, we can show that the energy per photon is 2.7 times Boltzmann's constant times temperature. We could start by guessing it's kT, but we'll start by guessing it's 2.7 kT. Plug that in to this expression that we got from setting the derivative to 0, and the right side should equal 2.7. Well, it almost does. Take that 2.798, put it back in the exponential, and you get 2.817. Do it one more time, put that 2.817 in, and you get 2.820, and we're getting really close. If you keep going, you'll find that h bar omega is 2.821 kT when you're at a peak. So h bar omega at the peak is 2.821 times kT. Instead of omega peak, write 2 pi c over lambda, and you have an alternative expression that lambda times temperature is hc over 2.821 k, or that lambda at the peak times temperature is a constant. That's Wien's displacement law, and for a hotter star, you'll have a shorter wavelength for the peak. For a cooler star, you'll have a longer wavelength for the peak.